I find this one of the most exciting developments in the world at this time, really. According to Janine, we're now learning how to grow food like a prairie, how to create color like a peacock, self-medicate like a chimp, compute like a cell, and run a business like a hickory forest. She says, quote, the more our world functions like the natural world, the more likely we are to endure on this home that is ours, but not ours alone. Janine BENYUS is a scholar, a science writer, an innovation consultant, and the author of 6 books, including Biomimicry, Innovation Inspired by Nature. And since that book's 1997 release, she's evolved the practice of biomimicry, consulting with sustainable business, academic, and government leaders. She's co-founded the Biomimicry Guild and the Biomimicry Institute and the web portal asknature.org. And all of that is to further this work of biomimicry. Her next book will be Nature's 100 Best Technologies. Welcome, Janine BENYUS.
Hi, Terry.
Good to be talking to you again. It's been a few years.
It has. Thanks for having me back.
Oh, you're very welcome. I remember when you were first on my show, the very first time was quite soon after the book had come out, when all of this was quite new. And for me, it's been wonderful to sit back and watch this sort of movement grow. I like listeners to get to know the people behind the work and the ideas that we talk about. So no one sets out to become a biomimicist, right? So what was your path?
It is true. Yeah, I'm as surprised as anyone about how this meme, this idea has made its way into the world. No, I wrote the book, and I basically was just, looking at, I had written 5 natural history books, and I specialized in plant and animal.
Right, and to give people a sense of how specific they were, it was the plants or the animals of a certain region of Montana or that sort of thing?
Well, yeah, it was wildlife habitats of the eastern U.S. and western U.S., but they were ecosystem first field guides. So, I'd say, what's going on in a ponderosa pine forest? If you go there and you pitch your tent, who are you likely to see? Because they're so well adapted there. Or the marsh animals, how well adapted they are. And when I look back at those books, it was just one amazing technological adaptation after another, or some amazing chemical ability, or some ecosystem strategy that I was always sort of marveling at. And I think at one point in about 1990, I said to myself, look, is anyone consciously here we are, we have all these invention firms all over the country, and every big company has invention, Skunk Works. Is anybody just walking outside the door and trying to emulate, what's already been done? I remember I thought about solar cells, and I thought, well, how do our solar cells work? And do they work like leaves? And the people, and I knew the scientists who were studying photosynthesis, and then I found out, lo and behold, that our PV cells don't work at all like photosynthesis, and there really wasn't any cross-pollination between the two, except I found this, one small group in Arizona doing this. And I just kept collecting, and I kept finding the people who were crossing over between the incredible technologies in the natural world, and who were trying to bring the design principles into our designs.
All right, but let me ask you, because it strikes me that if you're looking from one perspective, you're looking from the naturalist perspective, and you're creating a field guide, as you say, to the marsh or to the seaboard or something like that, and you're seeing all these things, but my guess is there must have been some moment when a switch went off in your head that said, I'm not just looking at how they populate this marsh. What if I looked, you know what I mean? That kind of thing. It seems like there was a shift of figure ground or something where what you were seeing and what you'd been looking at suddenly meant something new.
Well, it came from something all of us who, care about the planet, we do a lot of reading, which can be very depressing, and it was at a time when, our technological entrancement was just breaking down. I mean, we basically were like, all right, we're 20 years after Rachel Carson, and, that the alarm bells just kept on ringing. So I was reading a lot about what we did wrong, okay? And then I'm sitting in places. I live in Montana, and I'm able to live in amazingly beautiful places, walk across the valley and go into a wilderness area. And I look around and I say, hey, everything's working pretty well here, you know? and what it does, what the figure ground switch is you erase in your mind the idea that these organisms are not like us. What you say is, oh, they're exactly like us, in the sense that, you know, they need to meet their needs. So you look at a tree and you say, okay, it's pumping water, right? Well, it doesn't actually pump it. You know, it pulls it up with solar energy, but it's raising water up hundreds of feet. It's not like we raise water in our buildings. You know, we don't do it the same way. And then you say, okay, what else is it doing? It's gathering solar energy. The leaves are tilting like level-or blinds. They're tracking the sun. It's defending itself against pests. You know, it's handling winds and fire and flood. And, you know, it's an amazing, it's doing amazing things. And, you know, every organism I'm looking at are parents tucking their kids in at night. You begin to, you say, you know, you sort of dissolve this difference between them.
Right. In other words, what they have is they have circumstances, they have needs, they have problems that have to be solved. And as I pointed out at the start, tell me if I'm right, that one of the things that I remember when you said it to me, it was so, you know, a light bulb went off in my head, that for us to do these things, we often need extreme something, pressure, temperature, solvents, toxins, and nature does these things at basically room temperature, and it has a lot of time to operate, but it seldom uses enormous pressure. It seldom uses, you know, and so it's that interesting thing that it has some of the things that we found to jumpstart things or catalyze things or make things happen on our schedule or in the place we wanted were things that they don't have in their repertoire. And if we could learn to do things without some of those things we've been using, we'd be more sustainable. We'd be less polluting. We'd be more efficient. All of that, correct?
Absolutely. I mean, number one, you know, if a tree's sitting there in a forest, it's using whatever materials it's got at hand. So it's using all local materials.
It has no locomotion, right?
Right. You know, and it's sitting right, exactly, and it's so it's juggling those resources over and over again. Those materials are being juggled by the system over and over again. And you realize, wow, there's a very small subset of elements that life actually uses in the periodic table compared to us. We use every element, and we use very rough, sort of brute force strategies. We heat it up to high temperatures to force molecules together, or we beat it with, you know, high pressures or toxic chemicals that force things together or apart. Well, if your manufacturing plant is your own body, in or near your own body, you can't do that. If you're an abalone, you know, in the ocean and you need to grow a hard shell around yourself, you need to do ceramics, but you can't build a kiln and stoke it up. You know, you just can't. So but the interesting thing is that despite their really low energy fluxes and the fact that they do things literally in water instead of sulfuric acid as a solvent, life solvent is water. They do it in water. They do their chemistry in water, and then they do it at seawater temperatures, you know. And the thing is, they create a ceramic, the inside of an abalone shell, that mother of pearl that we use as jewelry. That's twice as tough as our high-tech ceramics you find in a jet engine. And, you know, the way we make things, I mean, it's just, you know, think about nature's cement or nature's concrete even. Something simple like concrete, you know, it's the most used building material in the world. But the sad thing is that 6 to 8% of all CO2 emissions come from making concrete.
6 to 8%.
Yeah,
comes from the manufacture of concrete. That's amazing. Okay, so we've kind of got, I think, a notion of what this is and what we can learn from them. What happens, just quickly, what happens at the Biomimicry Guild and the Biomimicry Institute? What those things that you've kind of founded along the way?
Yeah, the Biomimicry Guild is a for-profit, and it's a consulting firm. And we have 12 biologists, and the new career that we created is called Biologist at the Design Table. Mm-hmm. So we work with companies like Boeing, working on the new plane, and GE Healthcare and Kohler Plumbing and Interface Carpets and seventh generation cleaning products, and General Mills Food, pretty large companies that are trying to come up with new inventions. And they ask us a question like, how would nature reduce moisture, or how would nature reduce vibration, or how would nature remove blood from hospital sheets, and we do a large literature search, amoeba through zebra it's called, and because we go across taxa with that functional idea, and we find all the amazing strategies that life has evolved to do this, and not one of them has high energy,
right,
high fossil fuels, right? They're all very elegant, sometimes very, very simple, but we just haven't had enough evolution to come up with the idea. So then we present them to the company, and then they try to emulate that. So that's one of the things we do at the Guild. And then the Institute is our nonprofit. We realized we got to a point with our for-profit. The phone would be ringing, and it would be somebody from Herman Miller, talking about furniture, sustainable furniture. And then the next minute would be somebody from their, who had 8th grade homework they wanted us to help us with, So we said, we probably should do a nonprofit that can educate the next generation of biomimics, K through university, and so we started that about 3 years ago.
That's the Institute, the nonprofit part.
Yeah, that's where AskNature.org is.
Right. And AskNature.org, let's talk about that right now. Sure. When I was reading it, I see that you kind of debuted it in association with E.O. Wilson, and I've read about E.O. Wilson's big project being sort of a wiki of the universe, or of at least this planet. Are these two things, are these part of the same project?
We're collaborators. Yeah, what's happening is that Ask Nature, we realized that, we're 12 people and we're working with some companies, but our dream was, every inventor in the world should be able, at the moment of creation, to type in a function like filtration, filtering salt out of water. And they should be able to find nature's wisdom on that topic, and find the papers and the experts about seabirds or sea turtles or your kidneys, and all the different ways that life filters salt out of water. And it should be for free, a public domain. So that was our goal, our mission was to organize the world's biological information by function.
Right, that's a real
and engineering function.
For people who haven't thought about it, so much of biology, botany, and so on was defined by form, things that looked similar, had similar ways, similar, wings, or how many legs they had, those sorts of things. And your way of looking at things is across all of those toward function. Toward function.
How does nature deal with fire? We need fire. We need an alternative to fire retardants. What are all the ways that nature resists combustion? And not just plants, but animals and bacteria and fungi. And if you get a category like that, and what we did was we thought about all the sustainability challenges that are out there, and those are the functions we're trying to fill in first. And E.O. Wilson, in the meantime, he went to TED a couple years after I did.
Now, let me fill in a couple of blanks for people.
Oh, yeah.
So E.O. Wilson is one of the sort of eminent scientists in the world at Harvard for many years, best-selling author. And TED is a conference, technology, I think it's technology, entertainment, design were the original TED, three things. TED is a conference going on for, 20 years maybe now, where people with big ideas kind of come together. And they've moved in the last few years to really a focus on how can these big ideas help people and help the world.
Yeah. The people apply to have a wish fulfilled.
Right.
And so Ed Wilson, who, by the way, is my hero, he and Rachel Carson sort of got me off on my career as a naturalist. Anyway, so Ed Wilson stood up and said, I want to create a web page for every species on Earth, and I want to gather everything that's known about that species in an expanding encyclopedia. It turned out, they now have $50 million. It's a 10-year project, every scientist in the world is going to be putting in everything right from what we know at the molecular level all the way up. They're scanning all the natural history information way back to Linnaeus and Darwin when they were, writing stuff out. All of that will be, anything that a biologist ever said about a species, right, will be there. And so what we did, we went, got all excited about this and said, wouldn't it be great if they had a data field that said, what can we learn from this organism?
Yeah.
And while they were filling out EOL, they were also putting in this functional info. And then so they said, yes, of course, that's a great idea. So our site will vacuum that information up. And then our users are people, innovators of all stripes. And they'll be looking at that biological information and go, oh my gosh, I know a new way to move water up a building through capillary action. I'm going to design something and perhaps even, create a product. And that's what will happen. These sustainable products will be inspired by this information, and then that will go back to EOL. So people reading EOL, one of the things they'll read about is what this organism has taught us.
Mm-hmm. And EOL stands for?
Oh, I'm sorry, Encyclopedia of Life.
Oh.
Yeah, Encyclopedia of Life. So we're trying to organize the world's biological information by function.
Right. He's trying to gather all the world's biological information,
exactly.
and your piece of that is to gather it by function, which I think is so, let me ask a question, again, one that might come towards the end of the conversation, but it just is kind of getting to me. I'm sure, I often ask people who are deep into a field, I assume they think about it when they're hiking and when they're bicycling and when they're falling asleep. What's your take on why this is a new idea? How did we get so far with, it seems to me originally, this would have been the way the indigenous folks would have done things. They'd have said.
It was and is.
And now my off the top of my head guess is that we had the luxury of not being as elegant or efficient. At least it appeared to us that we did. So when we came up with a way that we could do it with enormous pressure, enormous heat, or toxins or something, that was fine because, wow, look at what we're able to do. And that it is necessity that's kind of pushing us finally to get more elegant, more efficient, more clean, more brilliant, and we realize nature has already done that work. Is that that's sort of my take. What's your take?
No, that's a beautiful summary of it. It's absolutely true. It's, the selection pressures. Natural selection works with these selection pressures, and these organisms, you're absolutely right. They don't have fossil fuels available to them. They have found a different way given what limits they have. They don't see it as limits. They see it as a set of opportunities in the habitat. What can I do with this, right? But it's limited, and you're absolutely right. When we started to dig into the Earth's crust and we got this fossil fuel, it put us on the end of a very long lever, and we were able to, oh my gosh, we were able to multiply our muscle power, almost infinity, we got very entranced with what we could do with this, and then, of course, we painted ourselves into this corner. And we have used a lot of the resources that were very abundant. They're getting scarcer and scarcer. So what's happening is...
And the other side of that, and the other side, just to interrupt for a second, the other side of that is that, as I mentioned at the top, is that the methods we used often produced side effects, produced pollution and so on, which, again, we didn't notice at first. But so we come upon the limits of resources and the limits of disposal and public health and climate change and all those things.
That's right. It's interesting. Herman Daly is an economist, and he says that, it made perfect sense for us when we were a small population in a large world, right, to spread out and be this pioneer species, like a weed species, just keep going and not really care about, putting down roots or recycling or trying to be more elegant, because we always had somewhere else to go.
Right.
Well, now we've circled the Earth and met ourselves, on the other side.
Yeah.
And now we have to switch our strategy. So if that strategy was what ecologists call type 1, a weed strategy, spread out, put up, have a plant body, make a bunch of seeds, blow off to the next opening, the next field. Literally blow your seeds away to the next. Don't stay there because you could be gone in a year.
Which is the way of a weed.
That's the way of a weed. That's what we've been doing. Well, now it's time because habitat conditions have changed on the Earth for us. It's time for us to adopt the strategy of this long-lived forest species, right? This type 3 species, which is figure out how to make the most of what is given locally. Don't fell your own nest because you'll be there for a while, And so all of a sudden design becomes more important than high energy and huge material throughputs. Designing, making really elegant designs both of on the form level and on the process level, like on the chemistry level, that becomes important for us to stick around on the planet.
I think of a book, The Ingenuity Gap by Thomas Homer Dixon, which I assume you're aware of.
Yeah.
And William, Thomas thinks pretty deep about this stuff. And, he says that basically we've always been able to ingeniously solve our way out of our problems. His question in that book is, have the problems gotten so complex or on such a scale that we can't? And what I hear in this whole thing around biomimicry is that there's a resource in a way we haven't tapped. So in some sense, if there's a reason for optimism, given the crises we face, it's that there are all these solutions, and we've been pretty smart so far at doing certain things. If we can be equally smart and ingenious, perhaps we have time to save ourselves and the others with us.
Yeah, I would think that the resource we have to tap first is our own humility.
Yes, humility.
We haven't really played with for a long time.
Yeah.
I think that back, those hunters and gatherers, the indigenous peoples who lived very close to the land, they had a certain biological vulnerability that they were very much in touch with.
Yeah.
And they looked around their habitat and went, wow, there are some species that are doing a lot better than I am, and I'm going to watch them, right? There was a humility. And I think we're getting back to that point where we're saying, okay, we could close ourselves in a room and rack our brains and try to come up with the next ingenious thing. But how has that worked?
Yeah.
It's a 50-50. We have great symphonies and medicine, but we also have these other things. So when we're looking for a solution that fits in a system, that already has been tested. We want something that's been tested and that's not going to have a lot of unintended consequences once it gets into a system. Well, every innovation in the natural world has been tested in context and for long periods of time.
Right. As I said at the top, the failures are no longer here.
Exactly. And they were, and it's no easy feat to have a technology that fits in. It's easy to have a technology that works, that one parameter. It goes fast.
Right.
But
it lifts big things. Yeah.
That's easy.
It makes
works.
a lot of light.
Right. But to have a plus, have a works and fits in,
right,
is what we're trying to figure out.
And now in this new era of limits, of the perception of limits, but because of population, because of pollution, because of climate change, because of peak oil, et cetera, now we have to get smarter, and it turns out, luckily, some of our fellow life forms have worked well within limits for billions of years. Let me shift the conversation a little bit, Janine, to some of the we've been dealing sort of with the origins and the foundations. Let's jump now to some of the manifestations. Who are some of the people you're working with? Have some types of organizations or companies proven easier and harder? What are some of the give us a list of actually some of the things that have emerged.
Yeah. Well, I'll tell you, the interesting point about this is that some of these companies don't want some of these things to be known because they're going to bring them out. But the ones that I can talk about, say a carpet company like Interface Carpet, they came out with a whole new way of doing carpet tiles so that instead of having and this was based on random order in the natural world, that we brought them out into a workshop and they looked at leaves on the forest floor. This was just a simple form mimicry. They realized when they picked up a leaf and they looked back down, nothing had changed, you know. And they said, what if every single carpet tile was different? Then we wouldn't have to worry about pattern, and if one got soiled, we could put a new one down and your eye wouldn't even recognize it. Well, that turned out to be, believe it or not, a huge innovation in carpet tiles. It's now 40% of their sales. So they said to them,
now let me see if I get this straight. I've studied interface. I've had Ray Anderson on the show and so on. Are you saying that this is? I mean, one of their first innovations was just the idea of carpet tile at all.
Yeah.
Right. Which for people to think about it, until people came up with carpet tiles, which means that your room or office is a bunch of smaller pieces of carpet. If you spilled something, you had to replace the whole carpet.
Right.
And so the innovation of just carpet tiles is pretty brilliant. But you're saying that this was a further innovation.
Yeah, because there was, believe it or not, there was a sore thumb effect. What they hoped was spill something on a carpet tile, send it back to us, we'll recycle it, send you a new one, and then there won't be all this carpet waste. Well, that's not what happened.
Oh, right, because the carpet you've got is 2 years old, the color's faded. Right,
a new one's down, it's like, never mind, pull it all up, throw it to the landfill.
Right.
So this really changed the equation. I mean, you could take the edges of the carpet roll and what used to be spare things you'd throw away because it didn't match the pattern, now you could use. So all of this stuff, plus, customers loved this because they could throw it down in any direction, and it was beautiful. So they said, okay, let's do more innovations like this. So the next thing they wanted to tackle was glue, because the other secret behind carpet tiles is that they glue them down. And when you want to,
you wouldn't have to do that if you got a full room of carpet. You don't necessarily have to glue it down, but you got to keep those tiles in place.
You got to keep the tiles in place. But they wanted to get rid of the glue, and they also wanted to seal the seams because they wanted to use it in hospitals, but bodily fluids would go down the seams, and so hospitals said no to carpet tiles. So we were having this workshop, and we had people at different tables solving different problems, and laid out before them were all these artifacts like shells and bones and skins and feathers. And the people who were talking about seams, we were showing them bird feathers and how bird feathers, have these hooks and barbules, and on the edges of each of the little barbs of a feather, each of the little pieces of a feather, they when a bird ruffles its feathers and then it takes its beak and it zips its feathers back together, that's putting it's like a zipper without metal, It's a self-closing feather, feather self-closing. So we said, well, what if you had the edges somehow be able to interlock? Well, this was a revelation, believe it or not. So that table was thinking about that. In the meantime, the other table was thinking about glue. How does nature adhere? And we kept coming back to these things. A fly doesn't use glue, and a gecko doesn't use glue. There's a certain amount of gravity and heft to the animal, and it does it through these really small forces, physical forces. So, believe it or not, the people who were doing the glue listened to the people at the other table with the bird feathers, and they said, wait a minute, if we hook all the tiles together, it'll become one long big broadloom like an area rug, and gravity will hold it down without glue.
Oh, right. Yeah. You go back to the way you did it before, only, okay, very good.
So sometimes a bio-inspired innovation comes just from, understanding simple mechanisms that are out there in the natural world. Other times it's mimicking. There's a company called Cambridge Biostability that said, okay, how do we preserve without preservatives? How do we make vaccines last for years and years and years without refrigeration?
Because the places that need vaccines the most often might be in short supply of refrigeration.
Yeah, because 50% of intended recipients never receive their vaccine because refrigeration breaks down between lab and village somewhere along the line. So it's millions of people, 10 million children a year, for instance, died with, that could have simple vaccine. So this guy, Bruce Rosner, said, well, what in the natural world preserves itself, that it doesn't use preservatives, it can't use toxic preservatives, it doesn't use refrigeration. So he looked at this plant called the resurrection plant that literally it dries out to the point where it looks absolutely dead, gray leaves, the whole bit, and it'll stay like that for months. And then you add a little water, it comes back green, and in an hour it's happy and photosynthesizing. Like, what is going on here? He looked into it, and he found out that it has this special sugar in its cells, and it's able to dry out, and as it dries out, it sort of turns to an amber kind of glassy substance, preserves the cells. So he said, let's mimic that with vaccines. And so now he's creating a vaccine, storage device, basically a vial of vaccines. You can throw it in your glove compartment of your car, last for years. I say to myself, my gosh, preserving food is such a huge, right? So it's those sorts of things. We sort of say, what does the world need? And what's a really bad design right now?
Right,
and then
right.
what in the natural world's doing it?
So that's a good place. In other words, big need, bad design.
Yeah.
This calls for. Let me. As I've been listening to you, I've been thinking about a few big ideas, which I want to. We got down to some very specific examples, which I really appreciate. When you can tell a story that is about real people in the world solving a problem, that really, I think, brings it out to people as to what we're talking about. But let me go back again, fly up a little bit in some of the bigger ideas. One thing that you've alluded to is that biomimicry, you sort of say, works at three different levels: the level of form, the level of process, and the level of system.
Yeah.
Talk a little about that.
Yeah, those are the three ways people are mimicking. I mean, you can mimic form, and literally, say you're mimicking a really streamlined shape in the natural world. Like there's a company that is doing called Biopower in Australia, and they're doing tidal generators. So as a tide goes out and in, it grabs energy. Well, it's to grab the energy. It mimicked the form of a tuna's tail. Because it's so streamlined, and literally it waves back and forth like a tuna's tail, and grabbing energy every single, there's a turbine or a generator associated with it, and that's mimicking a form, and you can do all kinds of things with that. You can mimic. There's this beetle in the desert in the Namib Desert that has these bumps on its wing scales, and it grabs fog out of. It grabs water out of fog with this form and a little bit of chemistry. So you can mimic a form, or you can mimic a process. Like there are now solar cells, dye-sensitized solar cells, thin-film solar cells that mimic a process called photosynthesis. And you can mimic chemical reactions, or you can even mimic natural selection itself in software. You can mimic the process by which bees find or ants find food. That's been mimicked in a lot of software optimization programs. And then the third one is mimicking at the ecosystem.
Mm-hmm.
So in this case, it's really how do you make a company, for instance, behave in its industry like a member of an ecosystem? How do you hook companies up into a food web so that whatever's coming in their door is something that's come from another company, a byproduct of another company, and they use that as a material, and then whatever goes out their smokestack or out what used to be their dumpster becomes a product or a resource,
an input, yeah.
So it's that mimicking things at an ecosystem scale. The other ecosystem mimicry that's really kind of exciting, one of the new things, since Terry, I don't think I've gotten to talk to you about this personally, but we're working with the largest architecture engineering company in the world. HOK is their initials. And what we're trying to institute there is something called ecological performance standards. And our feeling is if they touch, every year they get about 3,500 projects, they touch an area the size of Connecticut.
Wow. Yeah.
So if they're going to build a building and a project or even a development, our feeling is we should look at the native system, ecosystem that would be there, and say, how does that ecosystem, how many tons of carbon does that ecosystem sequester? And when it rains, how many gallons of water are absorbed and then slowly released over what period of time? How many degrees Fahrenheit does a native system cool the air or build soil in what period of time? How many inches of soil are built? And then those ecosystem services, and they go on and on, modulating climate and disease and pest control, and say, this is what the building and the project should do at least as well. As
if it weren't there at all.
Absolutely.
Yeah.
So at least as well as the native ecosystem, and that brings our standard of what we do in the built world, which is our largest artifact, that brings our responsibility way up, you know.
Now, is it possible to approach that?
We're gonna set those metrics. It's an aspirational goal,
right?
And in some cases, absolutely. If you look at how much sunlight, say, is gathered, you maybe with the surface area you've got on a building, you're able to gather that much energy and even above that and export some back to the grid.
Okay, I can imagine that. In other words, if what was there was only one surface, which was the ground,
yeah,
and now you have the surface of the roof, which is as big as the ground was, and you have the surface of the walls, which weren't there before, perhaps you can do better than just what was there.
Yeah,
okay,
or
that's exciting.
I think one of the things we're going to have to learn to do as a species is learn how to build soil. You know, our
wow.
our organic farmer friends, they know how to build soil. You go over to their house, and the first thing they do is they take you out to the backyard and they say, "Look at the soil, right? It's beautiful," and they're smelling it. They know how to build soil. As a species, we have to learn how to do that. So this whole thing of just sort of sterile landscapes, you know, outside of buildings, no. I mean, we need to create fertility where we live. You know, one of the most amazing... Have you seen the museum of the Native American Museum in D.C.?
No.
Have you gone there?
No.
Man, that's a beautiful building. But outside, there's thousands and thousands of different species of plants planted. And there it is, plunked right down on the mall, you know, next to the Air and Space Museum and all these other museums which have very sterile sort of lawns around them. And then all of a sudden you walk up and there's all these biomes and habitat types. So it's like a botanical garden or an arboretum around this building. And you think, and you're sitting there, you know, and there's a little wetland and birds are flying all around, you know, and you're having your little snack waiting to go into the museum, and you think, why aren't all buildings like this? You know?
Yeah, yeah.
Lush with life. And I think, you know, that's what we're going to head towards.
You've alluded to something a couple of times here called nature's services, which you know, I've talked about before in the show, but a couple of ways that it seems to me that comes in is, one, this goes back to your thing of function, you know, looking at things in terms of function. In other words, one of the insights, it seems to me, of modern companies is to realize that people don't want things, they want the services things give them. They want warmth, they want comfort, they want the ability to communicate, these sorts of things. And in nature, for a long time, it seems to me, we thought of nature as resources and not the services nature produces, like purifying water, purifying air, flood control, et cetera, et cetera, et cetera. Talk a little bit about services. And there's a level, I think that's at the level of the second or third one of process and system where you actually are dealing with the services, right?
Oh, yeah. Oh, yeah. Well, ecosystem services are just, it's all the things, you know, life creates conditions conducive to life, right? And it does this while meeting its own needs. All of those organisms in ensemble are making life more livable. So whether it's damping down pest epidemics or slowing waves, you know, mangrove forests slowing waves so that coastlines don't get eroded during tsunamis. That's a service that is very, once it's gone, boy, that's when we realize it. For instance, think about pollination as a free service.
As we've seen with the bee die-off of the last couple of years.
And then all of a sudden you go, oh, my goodness.
Yeah, in other words, it's as much as we think about, how will we replace a resource, a chemical, or if it runs out, or a metal.
Yeah.
That's what we weren't able to see, I guess, the forest for the trees, literally here, was that the service provided by nature are much more expensive or impossible to replace.
Oh, absolutely impossible. And, I mean, to the extent we're trying with ecological performance standards to meet it somehow, it's amazing how much engineering we have to put into trying to gather that much energy. We don't yet. Our solar cells don't look as gorgeous as a full, thousands of leaves on an oak. But no, that's when you get really humble, when you realize what the system is doing. And the other ecosystem service that I'm in terms of our consciousness as a species, one of the other things that life gives to us as a gift is this whole realm of wisdom. These ideas are really, to me, a new kind of service that we're starting. Well, it's not new, but we're in Western industrial culture.
We're coming back to
it, and we're going, wow. Not only is this system, making it possible for me to breathe, but it is also teaching me how to live here. And it's interesting, Terry, because I've been working now with United Nations Environment Program and World Conservation Union, some of these global NGO communities. And what they're doing, UNEP is looking at asset and benefit sharing, which is basically the biopiracy laws of 10 years ago, in which we said, when we go down to Costa Rica and we find a plant that has a drug in it, how should we recompense the indigenous people there, right, or the country? And now we're taking another shot at that, and there's COP10 coming up in 2010, and we're going to rewrite the asset and benefit sharing protocol. And, a year ago I came to them and said, hey, the other thing, it's more than just molecules, it's just these ideas. And how do we say thank you, right?
In other words, I get what you're saying. In other words, an organism or an ecosystem has figured something out.
Yes.
We not only benefit perhaps from the organism itself, but from learning from it what it figured out, who benefits from what we, who owns or controls or benefits from what we learned.
Exactly, because when you think about it, the organism is the patent holder.
Yeah.
You've got a blue mussel. It's been in the ocean for millions and millions of years. It's learned how to glue itself underwater. Well, now we finally mimicked the recipe, and we're using it, Columbia Forest Products. If you buy hardwood, plywood in this country, you're probably using a mimic of in the resin. Instead of having formaldehyde leaking out, they now have a waterproof glue that's based on or inspired by the mussel. Now, the mussel stays in the ocean. This is what's different about biomimicry. It used to be that we would harvest the mussel and grind it up.
Right.
We'd extract the stuff. Now, the mussel stays there. We study it. We borrow its idea. We're its student. We say thank you. One of the things we're doing at the Institute is saying, how can we say thank you in a more, how can we manifest our Thanksgiving? And we started this program called Innovation for Conservation, in which we're asking companies, it's voluntary, but we're asking companies that have a bio-inspired product to donate a percentage of their proceed to protect the habitat of the organism that inspired it. The original patent holder.
Right. Oh, one thing I've read about, I think the Business Week article mentioned this, was that one other thing that might flag your interest besides here's a problem, here's a bad design, is also if the species that we're learning from is endangered.
Yeah.
That actually makes them more attractive because they need if we take from them, they need us to recognize that.
Absolutely.
Yeah.
Absolutely. So it's sort of we like to, there's so many thousands of cool ideas out there that organisms have that really could help us. But we try to, when we pull things like for the Nature's 100 book, we try to pick organisms that that were on the red list. They are either threatened or endangered, because you read, you go to asknature.org, for instance, you read about this amazing organism, this thorny lizard that can wick water out of sand, and couldn't we do that to get water up in dry areas, and then you say to yourself, well, how is this amazing organism doing? And depending on the organism, you might find out that there's, 23 of them left.
Yeah.
Or, and you go, wait a minute. Then there's a little button on the site that says, thank a genius.
Mm. And the genius might be a non-human genius.
Yes, exactly. Yes, and then you click on that, and it says, here's the habitat that this lizard, it's the last place on Earth you're going to find this lizard, and here's a project of people living there who are really trying to protect that habitat, friends of the, spiny lizard habitat or whatever, and do you want to donate?
Well, one thing I also hear in that is that in some ways, in your way of operating, you're closing loops the way nature closes loops.
We call it a Thanksgiving loop.
Yeah.
I mean, it's basically, it's just good manners.
Yeah. One thing that's also occurred to me as we've been speaking is that, remember, we spoke at earlier about the timing. And the timing was that we humans could indulge ourselves in less elegant, less efficient ways of doing things because it looked like we had plenty of room, plenty of resources, et cetera, et cetera.
Yeah.
Not as much population.
Yeah, a long road.
So we're talking about the limit. But another thing that's interesting is we now have the computers and the technologies that allow us to learn things we couldn't have learned before. In other words, had we said, how do we mimic that mollusk? Or how do we mimic that lizard? Yeah. We might have said, wow, that's cool. Wouldn't it be nice? But have no way of actually learning how it did it. Am I correct that actually there's a fortuitous thing going on in the timing as well?
Now, we're lucky on this one. Because our need for this knowledge and wisdom is now matching our ability to actually ask the questions with these new scopes and tools and imaging and
modeling.
And biological knowledge is doubling every 5 years. Some fields every 24 months, and so we're gathering this amazing amount of biological know-how. And any scientist will tell you, for every question you answer, there's 15 that you realize you haven't answered. So but we are so much farther in terms of understanding, being able to see into the details, right? And at the same time, our ability to emulate these systems is coming online as well. Our ability to act at the very small level.
Right, that's what I was thinking.
How to do self-assembly.
Microbes are genius. I mean, Lynn Margulis' work talking about how, they invented the internet, they invented the interstate highway system, bees. But we know about it, bees and ants, but at the level of microbes. But now we have the computers and the instrumentation, the technological capability of actually learning what they have to teach us. Yeah.
Really, all we need is the humility. Really, because it's true. And the other thing is that there is the ability to see nature as model, and we also have to figure out how to see nature as measure. In other words, how to say, what wouldn't nature do, and pay attention to those signs as well. And then the last thing is nature as mentor. It's sort of the wisdom piece, because wisdom really is, you've got data that becomes information when you give it meaning, and it becomes knowledge when you put it into some sort of an application. And when you apply knowledge over long periods of time of trial and error and you synthesize it into some sort of a place-based understanding, that's wisdom.
Right.
Now, I think that the indigenous people had even though they didn't have the scopes, they spent a long enough time watching the system as a whole that they probably absorbed some of the larger life's principle lessons. Mm-hmm. Something we also teach companies about is, what are the meta principles, not the little principles of how molecules go together or how a material is made, but a larger thing about how organisms stay locally attuned and the importance of cooperation. And I think indigenous people sort of looked at those meta patterns and absorbed them. I think we need to develop sort of the scopes, if you will, the instrumentation that will allow us to see that level of wisdom, right?
Yeah.
Yeah.
So let me ask a couple of final questions. We've got about 3 minutes here. One is, I know that the book became a 2-hour special, The Nature of Things with David Suzuki. Is that something people can find if they're people that are more in tune to looking at a video than...
Yeah, that was Canadian Broadcasting Corporation, and Bullfrog Films carries it. And then there's also, there's a cost on that one, but I'll tell you, there's also there's a TED video. Pretty viral, and it's 25 minutes, and I was talking about 12 big ideas in biology.
So is it you plus slides?
Yeah.
Yeah, so it's not just your talking head, but it's you plus slides. So if they just go to, if they go to TED. What is?
Yeah, I think it's TED.com.
Yeah, but, and just go for the Janine Benyus talk.
Yeah.
Right. Okay, and by the way, if you, and you can go to YouTube also.
Or Ask Nature, it's on there too.
What's it called?
It's on Ask Nature.
But the name of it again was?
I think it's called, 12 big ideas from biology.
By the way, we mentioned TED earlier. For those of you who aren't familiar with TED, if you can go look up TED videos on a pretty regular basis, you will be inspired, you will have your mind blown, you will, it's people... They, on their videos, have some people like Janine, people like Dean Kamen, people like Craig Newmark, people who have come up with new ways of doing things, talking in pretty condensed form. I think they usually go for 18 minutes. So if you had 23, I think that's a long one, right?
Yeah.
So they're pretty bite-sized and pretty wonderful. So if you haven't looked into TED, the conference is outrageously expensive, but the videos are usually free to look at. Let me finally ask, okay, so we've got some websites, we've got a book, we've got a new book coming out. If a listener really wants to get up to speed with this, what would you say to them?
Well, I'll tell you, I would say go join AskNature.org. Because there's a lot of people who are interested in this topic. Go join it. And join the other people who are starting to upload stuff and what they're doing. And it's a social site as well as a library, digital library of ideas. It's really a social site. So join that. Join other people. And we have news crawls on there. And, it's basically Biomimicry Central. Okay,
so in other words, last year there wouldn't have been as good an answer to this question.
Oh, yeah, no kidding. The phone was ringing and we were saying, we'll send you something,
Yeah.
No, now it's not only us delivering sort of what's the latest in biomimicry, it's the community itself speaking.
So it's the people who are in tune with that perspective, who are trying to figure out that perspective, who are trying to look at things that way, coming together and learning from each other.
Yeah, uploading their designs, uploading their design challenges, uploading their what organism they're working on. It's a Web 2.0 project.
And that is asknature.org. So again, the book is Biomimicry, Innovation Inspired by Nature. The websites are biomimicryinstitute.org and asknature.org. And thank you, Janine Benyus. Keep up the good work.